Methods for obtaining coherent sources. In Young's double slit experiment, we have obtained two coherent sources by making the light from a single source pass through two narrow slits. So there are two other ways to get two coherent sources, and we will discuss some of those here. Now, Lloyd's mirror, that is first method. This is an extensively used device. The light from a source is made to fall at a grazing angle on a plane mirror as shown in figure 7.2. Some of the light falls directly on screen as shown by the blue lines in the figure, and some light falls after reflection as shown by red lines. The reflected light appears to come from a virtual source, and so we get two sources. They are derived from single source and hence are coherent. They interfere and an interference pattern is obtained as shown in the figure. So note that even though we have shown the direct and reflected rays by blue and red lines, the light is a monochromatic having a single wavelength. Then Fresnel biprism. A biprism is a prism with vertex angle is nearly 180 degree. It can be considered to be made up of two prisms with very small refracting angle ranging from half minute to 1 degree, joined at their bases. So in experimental arrangement, the refracting edge of biprism is kept parallel to the length of the slit. Then monochromatic light from a source is made to pass through the slit S as shown in figure 7.13 and fall on the prism. So two halfways of biprism from virtual images. So two virtual images forms which are S1 and S2. These are coherent sources having obtained from a single secondary sources S. So the two waves coming from S1 and S2 interfere and form interference fringes like that in Young's double slit experiment in shaded region shown in the figure. So whatever the shaded region, that is your interference pattern, that is superposition region, in short we call it. So optical method behind that. The phase of light wave having angular frequency omega and wave vector k traveling in vacuum along the x direction is given by kx minus omega t in equation 7.11. Remember that wave vector k and angular frequency omega are related as k equal to omega upon v, v being the speed of wave which is c in vacuum. If light wave travels a distance delta x, its phase change by delta phi, that is k delta x, which is equal to omega delta x upon v. If wave is traveling in vacuum, k equal to w upon c and delta phi is equal to w delta x, that is omega delta x upon c. So in case of wave is traveling in a medium having a refractive index n, then the wave vector k dash and angular frequency are related. K dash is equal to omega upon v, and we know that v is equal to c upon l. Okay, so v being the speed of wave in this medium. Thus, if wave traveling a distance delta x in this medium, the phase difference generated will be delta phi dash is equal to k dash delta x and omega n delta x upon c, which is equal to omega delta x dash upon c. So where delta x dash is equal to n into delta x. Thus when a wave travels a distance delta x through a medium having refractive index of n, its phase changes by same amount as it would if the wave had traveled at a distance n delta x in vacuum. So we can say that a path of length of delta x in medium of refractive index n is equivalent to path length of n delta x in vacuum. So n delta x is called optical path traveled by a wave. Thus, optical path through a medium is the effective path traveled by light in vacuum to generate the same path, same phase difference. So in vacuum, optical path is equal to the actual path travel as n equal to 1. Where optical path in medium can also be defined as the corresponding path in vacuum that light travels in same time as it takes in given medium. So time is equal to distance upon speed. So T equal to d medium upon v medium, which is equal to d vacuum upon v vacuum, and that is optical path, which is equal to d vacuum, that is v vacuum upon v medium into d medium. So n into d medium, that is your optical path. Thus, at a distance d travel in medium of refractive index, n introduces a path difference, that is n d minus of d, that is d into n minus 1 over a ray traveling equal distance through vacuum. So two waves interfere constructively when their optical path lengths are equal or differ by integral multiples of wavelength. And if we introduce a transparent plate of thickness T and refractive index n in front of slit S1, then the optical path traveled by wave along S1P is higher than that traveled by wave along S1P. In absence of plate by N1 minus T, N1 minus 1 into T. Thus, the optical path lengths and therefore phases of the rays reaching the midpoint O dash from S1 and S2 will not be equal. Then path lengths will be equal at point different than O dash, and so bright fringe will not occur at O dash but a different point where the two optical path lengths are equal. Then the dark and bright fringes will be situated symmetrically on both sides of the central fringe. So the whole interference pattern will shift in one direction. And on the basis of that, we have studied that interference pattern, okay, about that term. Now we have to see about diffraction pattern. Okay, now if you consider that diffraction pattern, okay, so again there are two types of diffractions. Okay, one is the Fresnel diffraction and another one is the Fraunhofer diffraction. So first we will see about diffraction of light. Okay, what is that diffraction of light? We know that shadows are formed when paths of light is blocked by an opaque obstacle. Entire geometrical optics is based on rectilinear propagation of light. However, as discussed earlier, the phenomenon exhibited by light such as interference can only be explained by considering the wave nature of light. Diffraction is another such phenomenon. In certain experiments, light is seen to be bent around edges of obstacle, so in its path, and enter into region where shadows are expected on the basis of geometrical optics. This is so-called bending of light around objects is called the phenomenon of diffraction and is common to all waves. So we are very familiar with the fact that sound waves travel around obstacle, as we can hear someone talking even though there are obstacles. Example, a wall placed between us and person who is talking. As we will see below, light actually does not bend around edges in diffraction, but is able to reach the shadow region due to emission by the secondary sources of light on edge of the obstacle. The phenomenon of diffraction is intimately related to that of interference. Diffraction is essentially the interference of many waves rather than two which we have encountered in interference. Also, diffraction is noticeable only when the size of obstacle or the slit is of the order of wavelength of light. Then, diffraction is a wave phenomenon. It is applicable to sound waves as well. As the wavelength of sound waves are larger, diffraction of sound is easier to observe. So this is nothing but the diffraction term. Now Fresnel and Fraunhofer diffraction. Diffraction can be classified into two types of depending on distance involved in experimental setup. So Fraunhofer diffraction. If the distance between primary source of light, the obstacle slit causing diffraction, and the screen for viewing the diffraction pattern are very large. The diffraction pattern is also called Fraunhofer diffraction. In this case, the wavefront incident on the obstacle can be considered to be a plane wavefront. So for this, we generally place the source of light at focus of convex lens so that a plane wavefront is incident on obstacle and another convex lens is used on the other side of the obstacle to make the pattern visible on the screen. So figure 7.14, this figure shows the arrangement of Fraunhofer diffraction. Second, Fresnel diffraction. In this case, the distances are much smaller and the incident wavefront is either cylindrical or spherical depending on the sources. So a lens is not required to observe the diffraction pattern on the screen. So in figure 7.14 shows a monochromatic source of light S at the focus of a converging lens, ignoring aberrations, means errors in mirror, lenses. The emerging beam will also consist of plane parallel rays resulting in plane wavefronts. So these are incident on the diffracting element such as the slit. So circular aperture, a double slit, a grating, etc. Emerging beam is incident on another converging lens that focuses the beam on a screen. So in the case of circular aperture, S is the point source and lenses are biconvex. For linear elements like slits, grating, etc., the source is linear and lenses are cylindrical in shape so that the focus image is also linear. In either case, a plane wavefront, as if the source is infinity, that is approaches and leaves the diffracting element. This is as per the requirement of the Fraunhofer diffraction. So we will see its Fraunhofer diffraction, by its diagram. So below figure 7.15 is the diagram. In figure 7.14 shows the cross section of plane wavefront YY dash incident on slit of width AB. The center of the slit is in point O. As width of slit is in the plane of the paper, its length is perpendicular to the paper. The slit can be imaged to be divided into a number of extremely thin slits. The moment of plane wavefront reaches the slit, each slit elements become the secondary source of cylindrical wavefronts responsible for diffraction in all possible directions. A cylindrical lens with its axis parallel to slit kept next to the slit converges the emergent beam on the screen kept at focus. The distance D, capital D, between slit and screen is practically the focal length f of the screen of the lens. So for all practical setups, the width A of slit is of the order of 10 raised to minus 4 to 10 raised to minus 3 meter and distance capital T is of the order of 10 meter. So D is very greater than A. That is very important. Now location of minima and maxima. So in figure 7.15 is a part of figure 7.15 is a part of figure 7.14. It shows two sets of parallel rays originating at the slit elements. The central and symmetric beams focuses at the central point P0 directly in front of O, the center of the slit. So rays parallel to the axis from all the points from A to B are focused at central point P0. Thus, all these rays must having equal optical paths. Hence, all these arrives at P0 with same phase and thereby produce constructive interference at P0. So, in case of point P at angular position theta, the optical path lengths of rays from A to C till point P are equal as AC is normal 2 a.m. So that we will see in diagram also. So I will show you that diagram so that you will realize how it works. So from this point onward, there is no path difference or phase difference between these rays. Hence, the path rays between AB and AC are responsible for net path difference or phase difference at P. So the path difference between extreme rays, that is BC, is equal to A sin theta. So let this be equal to lambda. Let K be the midpoint of AC and KO is equal to half of BC. So you can notice that KO is the half of BC, which is equal to lambda by 2. Thus, the path difference between AP and OP is lambda by 2. As a result, these two rays produce a destructive interference at P. Now consider any pair of points equidistant respectively from A and O, such as G and H separated by a distance A by 2 along the slit. Rays from any such pair will have a path difference of lambda by 2 at P. Thus all such pairs of points between AO and BO will produce destructive interference P. So this makes a point P be the first minimum. So this discussion can be extended to points on screen having path difference 2 lambda, 3 lambda up to n lambda between the extreme rays reaching them, and it can be seen that this point will be dark and hence will be position of dark fringes. Again, the same logic is applicable for the point on the other side at P0. Okay, so we can apply to it also. Hence, at the location of nth minima, the path difference between the extreme rays is what? A sin theta. Okay, A sin theta is equal to n lambda, which is plus minus n lambda. So if we assume the maxima to be in between the respective minima, we can write the path difference between the extreme rays at the nth minima, that is A sin theta is equal to plus minus n plus half of bracket complete and n to multiply by lambda, which is required equation. So in reality, okay, these are nearly midway, not exactly midway between the dark fringes. So in this way you can calculate different distances also. Okay, so distances of minima and maxima from the center bright fringe points. So equation 7.26 and 7.27, okay, these previous equations relate the path difference at the location of nth dark and nth bright points respectively. As described earlier, capital D is very greater than A, hence the angle theta is very small. Thus, if it is expressed in radian, we can write sin theta is approximately equal to tan theta, which is equal to theta approximately, that is y upon d, where y is the distance of point P on the screen from the central bright point. So the screen being at distance d from diffracting elements, that is a single slit. So let YND and YNB be the distances of nth dark point and nth bright point from the central bright point. So at the nth dark point on either side of the central bright point, equation 7.26, so theta ND is equal to YND upon D, where is equal to n lambda upon A. So YND is equal to n lambda D upon A, which is equal to n W, and also nth bright point on either side of the central bright point. So theta NB is approximately equal to YNB upon D, which is approximately equal to n plus half of lambda upon A. So YNB is approximately equal to n plus half lambda D upon A, which is approximately equal to n plus half of W, where W is equal to lambda D upon A, is similar to the fringe width and in the interference pattern. In this case also, it is the distance between the constructive bright fringes and constructive dark fringes except the central or bright fringe. So width of central bright fringe is what? Central bright fringe is the spread between first dark fringe on either side. So width of central bright fringe is the distance between the centers of first dark fringe on either side. So width of central bright fringe is nothing but what? WC is equal to 2y1d, which is 2w is equal to 2 times of lambda d upon a. So which is the first width, okay, of central bright fringe. Fine. Thank you.